Welcome back. This is lecture 25. So let's continue our discussion on distortion. But before going forward on talking about how to minimize distortion or what are the techniques that are used to minimize distortion, let's close the discussion with what happens if you have a cascade of systems, right? So till now, what we have done, we have done a noise analysis for a single system. We have done and we got to know how to analyze, or rather how to characterize the distortion characteristics of a single system. But when you are or a single block, but when you are making an overall RF chain, you know that there are multiple blocks that have to be put in cascade, right? So ultimately, as a user, I am interested in what is the end-to-end metric, right? I'm not really interested in what this particular block is doing. I'm interested in what the entire RF chain is doing. So while it is, as a designer, it is important to understand what is the noise figure of one block or what is the IIP3 of one block, so that I can get the idea of the SFDR or the dynamic range for that matter. But for the overall user, it really doesn't matter what these characteristics for one block is. We need to understand what is the overall performance metric, right? So which essentially means that we need to understand what happens to these blocks when we put them in cascade, right? So I'll not derive all the expressions, but I'll give you the framework how to think about it, and we'll get some intuition from that, right? Okay. So since we were discussing about distortion, let's start off with what will be the effective IIP3 if I put two blocks together who have different IIP3 numbers, right? So what I am essentially saying is that, let's say I have one amplifier which has, let's say, a linear gain of alpha 1. So this is, let's say, this is voltage gain. This is linear voltage gain of alpha 1, and it has an IIP3 of AIP31, right? This is again linear, right? Not in dB, in linear. Okay. And let's say I have another block right, which has a voltage gain of alpha 2 and an IIP3 of AIP32, and I put them together, and I'm interested in finding out what is the AIP3 of, or is the IIP3 of this entire block, right? So the easy thing to find out is what is the linear gain. What is the linear gain? The linear gain is alpha 1, alpha 2, but what is the IIP3? This is what I am after. Okay. So before I give you the expression, how will you go about, if I have to use brute force method, how are you going to figure out what will be the linear, what will be the total IIP3? So again, just like we had done for a single system, we'll have to put two tones at omega 1 and omega 2, right? Cosine omega 1 t, cosine omega 2 t, right? And I'm going to get a big trigonometric identity, and at the output of, which essentially means that here at the output of the first block, I'm going to get an output of at omega 1, omega 2, and I'm also going to get outputs at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Now these four tones are the input to the next block. So obviously, as you can see, I'll get a much bigger terms at the output, but most of the terms we can neglect because the dominant terms will be the fundamentals at the output of the first block, right? So if I say So this will be alpha 1. If this is VP1 or VP, so the input is, this is a VP, this will be alpha 1 times VP, and I am going to get some IM3 tone, right? So let me call this IM3 1. Similarly, at the output of alpha 2, what am I going to get? If the output of alpha 2 is perfectly linear, what am I going to get? I'm going to get this term, which is alpha 1 alpha 2 times VP, and I'm going to get the IM3 terms, but the IM3 tones will be basically a scale version of the IM3 of the previous stage, right? So this will be alpha 2 times IM3 1. This is assuming no distortion, but if I have a distortion, which the assumption is that we have a distortion, which means these two terms, that is alpha 1 alpha 2, or rather this alpha 1 VP term at the input of the second block is going to create IM3 tones separately, which will fall on the same IM3 on the same IM3 bin. So you have to add up these two tones, and if I neglect the potential phase shift that can also happen when adding this up, then I am going to get an expression, and that expression is something like this: 1 by AIP3 square is equal to 1 by AIP3 1 squared plus alpha 1 squared by AIP3 squared. Right? By the way, this is an approximation, because this we have to neglect many of the terms and make a lot of assumption that there no phase shift and all those things. Right? Then you get this term. Right? So I'm not interested in the algebra. I am more interested in understanding why this term makes sense and what is the intuition behind this. Right? That is what we are going to talk about next. So let's take it one step at a time. So let's assume that the second stage is completely linear. If a stage is completely linear, what would you assume its IIP3 to be? Or rather, not assume, what will its IIP3 be? Its IIP3 will be infinite. Right? If that is completely linear, means IM3 is not generated, which means IM3 never connects to the fundamental. It essentially means that it connects to fundamental at infinite, which means the second stage will have no distortion at all, which means it's like saying that I have a nonlinear block. At the output of the nonlinear block, I put an ideal linear block. So then what will be the overall distortion matrix? What will be the overall IIP3? Obviously, the overall IIP3 will be the IIP3 of the first block, right? Because that is the only distortion block, which essentially, I mean, now if I stare at this equation, does it make sense? Yeah, it makes sense, because if AIP3 2 is infinite, then the overall IIP3 of the entire block is the same as the IIP3 of the first block, right? Now let's do the other way around. Let's assume that the IIP3 of the first block is infinite. That is ideal, right? If the IIP3 of the first block is ideal, what is this telling us? This is telling us the IIP3 of the overall system is basically alpha 1 is basically AIP3 2 divided by alpha 1, right? So it looks like the IIP3 of the entire system has gone down. In the second block, moment I put a gain block before a nonlinear block, which is indicating that the distortion characteristics of the overall system, at least the input referred distortion characteristics of the overall system, has gone down. Correct? So why does it make sense? This should make sense. This is similar to the P1dB example with ideal blocks that we did in the previous lecture. So again, if I take the same example, so when I do IIP3 and let's say I have an input which has tones at omega 1 and omega 2 of value Vp. I have the same block where the input is gained up by some value alpha 1, voltage gained up by some value alpha 1, and then fade here. So what do you see here? The input strengths will be alpha 1 times Vp, right? So as far as this block is concerned, right? As far as this block is concerned, with respect to the input, what is it saying? That with respect to the first block, I am seeing that the input is seeing lot higher voltage swing, right? So in the top case, if the voltage swing is something like this, in the bottom case, the voltage swing will be much higher for the same input swing, right? So for this, that's the key thing to understand, for the same input swing, isn't it? So when I refer, so which essentially means that for the same value of input, the second case is going to create stronger distortion tones because the input is experiencing large swing, right? So essentially its overdrive is getting modulated and it's generating more and more distortion tones, and which naturally should mean that larger the gain of this block, more will be the effect of distortion at the output, right? However, if I say that at the output side, the OIP3 is constant, right? If the output side, if I say that the OIP3 is constant, let's say at the output I know that my IIP3 is, or OIP3 is equal to some amplitude OIP3 in linear term, which essentially means that when I have an input which is equal to input to this block, which is equal to A OIP3, the fundamental and the IM3 tones are identical, right? So this means that this V input, this means that when V input is equal to A OIP3, the output IM3, extrapolated output IM3 is equal to the fundamental, correct? Or rather IM1, right? So now can you comment on for what value of Vp in the case, in the lower, in this schematic, will you reach this value of OIP3? Clearly, it will reach that value of OIP3 when when input is Vp by, I should say this is V in, not Vp. When V in is equal to Vp over alpha 1, right? So that is why in this case your OIP3 or rather IIP3 will be A OIP3, or rather just IIP3 in the bottom case will be equal to IIP3 the top divided by alpha 1, right? So it should make sense intuitively, and it also makes sense if I stare at this equation, because if you see that if the first block is perfectly linear, that is does not have any distortion, which means AIP3 is infinite, then your AIP3 of the entire system becomes AIP3 of the second block divided by alpha 1, right? So pictorially this essentially means this: if you have one amplifier here, second amplifier here, as the signal moves through this amplifier chain, it amplifies. I mean, obviously its voltage swing keeps on getting larger and larger, right? And if I check at the output of the second stage, it will become again larger. So if I have another amplifier, this third amplifier will see even larger voltage swing, right? Which essentially means that subsequent stages of amplifiers are going to create more and more distortion components, right? Which naturally means that if you are cascading, it has two implications. One is that the input referred IIP3 obviously reduces, but that need not necessarily be a bad thing, right? In fact, that's not a bad thing in general, because it is expected that if the gain is high, the input referred IIP3 will be low, because ultimately you are operating with a fixed voltage supply, right? So that is why it is not sufficient only to say my IIP3 is this. You'll just like P1 dB, you'll also have to say that given that IIP3 is this, my gain is also this much, right? So without these two information simultaneously, this does not make too much sense, just quoting that number. Okay. And the second thing is, rather, if you have cascades of blocks and you know that you are getting gains progressively, then it obviously the blocks which are coming further down the signal chain must be more and more linear with respect to the blocks which are at the back end of the signal chain, or rather at the front end of the signal chain if I am talking about a receiver, right? So the first stage of the LNA can afford to be slightly less linear than the second stage if there is a second stage and that is available, right? So that's the key takeaway discussion. The second thing I want to talk about before I move on is this is as far as what is the effect of distortion in a cascaded system is concerned. But similarly, we cannot, I'd be amiss if I said that if I do not, what is the effect of cascaded systems on overall noise figure, because the noise is an equally important metric in an RF chain, right? So let's do that. So basically what we'll do is we'll assume the same thing. So this, I have one block which has, let's say, a gain of G, and it has a noise factor of F, or let's say I call this G1 and F1. Again, before I proceed, I would like to refresh your mind with respect to these definitions of G. So G1, G is a power gain. And I would like to, it's not a voltage gain, it's a power gain. And I would like to use a particular type of term here. I would like to use the term called available power gain. You'll call it GA, which is by definition is, I would like to define it as the power delivered at output under matched condition divided by power at input when input is matched, right? So as you already know by now that in RF system, generally we try to match the interfaces, especially if there are long routings associated with interfaces. If that is the case, then the assumption is, if I have a voltage gain, let's say I have a voltage gain of A1, and the input and the output terminals are matched. Say this is R, this is R, and I am driving a voltage source with resistance R, and there is a load of resistance R, right? So under this situation, whatever gain I get, power gain I get, is basically the available power gain, right? So this is, so in this, under this condition, your P out over P in is GA. Okay. So in this case, what will be GA? I mean, very easy to figure out. So this voltage is V in by 2, which means your P in available. So under matched condition, the available the power at the input is called the available power, right? Available power from the source, right? So this is also an important definition. So this is equal to how much? This is, if I use RMS values of V in, then it basically becomes V in by 2 whole squared by 1 by R, right? And similarly, your available power at the output, that is under matched condition, P out available is equal to, this is V in by 2 times A1 times 1 by 2 is a voltage across the output resistance whole square times 1 by R, right? So this is essentially V in by 2 whole square times A1 square by 4R, right? So your available power gain is essentially GA is, which is capital A, it's the protocol. V in by 2 whole square divided by R is GA. So this becomes A1 squared by 4, right? So this typically is the available power gain, right? Okay. Okay. So under matched condition, if I understand this is matched, so why am I interested in doing this matched thing? Because all these noise figures and factors are under the assumption that there is certain load impedance, and the load impedance, or there is source impedance, and the source impedance is generally the 50 ohm, right? So that's why these background assumptions are often necessary. Okay, so now let's get to our analysis. So analysis is actually quite simple once we make these assumptions. So let's say this the first one has a available power gain of G1A and the noise factor of F1. So what is the noise factor of F1? What does it mean? So this means that noise factor of F1, it means total output noise by noise due to source, which means there is a source which is creating noise and which is interfaced here, and F1 is with respect to that source resistance. Okay, and we have assumed everything is matched, so source resistance is also R. So this is equal to, basically total output noise is the noise due to source plus noise due to your amplifier, right? So we essentially means 1 plus a noise due to amp, or rather in this case output noise due to amp divided by output. So this is also output noise due to source. So which essentially means that your output noise is equal to output noise due to source multiplied by F1 minus 1, right? So what is output noise due to source? That is 4 KTR, right? Times the gain, the power gain, times F1 minus 1, right? This is the total output noise, correct? If I want to refer it back to the input, right? So which means that input referred noise is basically I divide by the power gain, so that becomes 4 KTR times F1 minus 1. Okay, so which essentially means that this block diagram of G1A and F1, I can assume it to be, where this is noisy, I can assume it to be a noiseless G1A, and then input referred noise which is added, which is 4 KTR times F1 minus 1, under the assumption that the input side is connected with a resistance R, right? So this is noiseless. Okay. So now what are we going to do? We are going to use the same model for another amplifier which has been put in cascade, and the model now becomes this. So if I put everything together, let's say this is the first amplifier having an available power gain of GA and noise figure of F1, which means that I can add it here as the added noise is 4 KTR times F1 minus 1, and I have another block which has a gain of GA2 and the noise figure of F2, and I'm assuming all the interfaces are matched. This is 4 KTR F2 minus 1, and again you have a matching resistor and everything, right? So we assume this is what it is. Let's say the matching resistor is a part of GA2, right? And this is your RS, this is R, and this is the noise from the source, right? So if I am finding out the noise figure of this, right, if I have to say this is, so the assumption is that all the GAs have been modeled like this, right? All the GAs have been modeled like this amplifier. So now if I have to find out the noise figure, so how do you go about finding out noise figure? We basically find out the total noise at the output and then only take out the noise from the source and then use that formula, right? So total noise at the output is 1 plus noise due to everything other than the source divided by the noise due to the source. Now what is the noise due to the source? Noise due to the source is 4 KTR times GA1 times GA2, correct? And what is the noise due to everything else? So noise due to this 4 KTR F1 minus 1 is 4 KTR F1 minus 1 and times GA1 times GA2 plus noise due to 4 KTR F2 minus 1 is 4 KTR F2 minus 1 times GA2. So essentially your noise total output, sorry, this is not an output now, this is a noise figure. The noise figure of the entire chain becomes 1 plus F1 minus 1 plus F2 minus 1, which is F1 minus 1 by GA1. So this is F1 plus F2 minus 1 by GA1. This becomes your noise figure of the cascaded system, right? So firstly, what does it tell you? It basically tells you that the noise factor of the subsequent stages, right, of the latter stage gets divided by the gain of the first stage, right? And if the gain of the first stage is high enough, right, if GA1 is much greater than 1 and F2 and F1 are of similar values, then you see that the noise figure of the entire chain is essentially the noise figure of the first stage, right? So if that is the case, then clearly it seems like the noise figure of the subsequent stages do not matter as much as does the noise figure of the first stage. Now this is quite the opposite with regards to distortion. In the distortion characteristics of the subsequent stages mattered, but in case of a noise figure, the noise figure of the first stage matters. And why does that make sense intuitively? Similar to distortion, it should make sense because if you think about it, what does cascading stages do? So if you think about it, you have a signal. If you think from the perspective of, let's say these two are identical stages, right? Let's say these two are identical stages and you have noise contribution from this stage, which I am showing in orange, and I have a noise contribution from this stage, let's say, which I am showing in red, right? So what happens after GA1? What do you see here? You see the noise contribution of the first stage gets amplified and appear at this stage, right? So here you are going to see something like this. So now at the output of the second stage, what are you going to see? Obviously, the output of the second stage, both this yellow and the red ones are going to get amplified identically. So essentially this, say I copy this. Okay, a scaled version of the input. And what about this? Right? But as you see that, because the first stage noise gets scaled, gets multiplied, it's gained up twice, and the second stage noise essentially get gained up once, at the output the first stage noise will dominate. So if the gain of this guy is higher, if GA1 is higher, if GA1 increases, then this noise contribution will increase further, and it will almost seem like the total noise is dominated by the noise of the first stage and not the second stage, right? So that is why the gain of the first stage matters. The technical way of talking about this is essentially the fact that the noise of the subsequent stages gets attenuated by the gain of the first stage, right? So that's essentially, even though it doesn't, when you make the statement, I am talking about an input referred noise, because in principle the noise doesn't get attenuated, right? It is only when you refer it back to the input it gets attenuated. But noise figure essentially is trying to give an idea of what is the contribution of the source noise with respect to the rest of the noise, right? And because the source is also connected with the input, it kind of loosely gives you an idea of input referred noise, right? So similarly, if you have multiple of these blocks having GA1 F1, GA2 F2, GA3 F3, and all of them are matched interfaces and all, the total noise figure will be the noise figure of the first block plus, or noise factor of the first block plus noise factor of the second block minus 1. Why that minus 1? The minus 1 is only taking out the effect of the source and only giving you the noise contribution by that block, divided by the gain of the first stage, plus then again noise contribution of the second block divided by, now the first block and the second block forms a combined gain stage, so the gain of the previous two stages, and so on, right? So as you see that the noise contribution of the subsequent, if you have a gain more than 1, the noise contribution of the subsequent stages become less and less relevant, right? Okay, so now, so basically what have we learned? We have kind of then made our peace with the fact that if we have a cascaded systems, the input referred IIP3 is going to decrease if we have gain subsequent at the further down the signal chain, and your noise figure will kind of not get affected at all, if because the noise figure is going to be determined by the noise figure or the noise factor of the first stage, right? So these are the two important things that you need to keep in mind when you evaluate a block, right? Let's say you are evaluating a receiver and it is told to you that it has an IIP3 of some minus 20 dBm and noise figure of 3 dB. Would you consider it's a good or a bad block? You should say that I do not have sufficient information, because you have to also give me the gain, right? An IIP3 of minus 20 dBm with a gain of plus 20 dB is probably not as bad. It's pretty good if I say that I have IIP3 of 0 dB and a gain of minus 3 dB, right? So these are some of the pitfalls that you need to be mindful of while evaluating a block, right? So before we end the discussion on noise figure or cascaded systems, so you saw that this analysis I have done by assuming all the interfaces are matched. But in practice, generally when things come inside the chip, they are hardly ever any match, because you hardly ever get any matching, because ultimately the matching is required if the length if the amount if the length of the wire through which the signal has to travel is of the order of the wavelength of the wire, right? But inside the chip, that is not necessarily true. So, which means that you can have this lumped element model and you don't have to do matching. So then all this analysis becomes, you can still do this analysis assuming exact, finding out the exact amount of loading and so on and so forth, but that becomes cumbersome. So the recommendation is, when you do not have matching, when you know that there is no matching in place, you do not use this formula that I have just shown. By the way, this formula has a name. It's called the Freeze equation, right? Goes by the name. It was first who proposed this expression. But having said that, let's say you have an interface where only the one of the ports are matched, the others are not matched, right? The typical case is an RF receiver where the input of the LNA will be matched. Output, if the LNA is followed by some blocks which are sitting next to the LNA and they do not have a long routings, then you probably don't need to match, right? So in that case, this equation directly doesn't hold as is. There are a lot of churning that needs to be done. So the better thing to do, or the most useful practice is, don't use this equation, but you do the full-blown analysis, assuming that the entire block is a block, right? And then finding out what is the noise figure. For example, I'll not do the analysis here. You can do it at your end, and we can maybe give it in one of the assignments. It's a good practice problem to solve. So let's say I have a common gate configuration, right? And the input is matched, and this is L. Assume this L tends to infinity for our purposes. And also here you have an L. Assume L tends to infinity for our purposes. And let's say this is followed by a common source amplifier, and it also, or maybe it also has an L where L tends to infinity, right? So neglecting CLM and parasitic capacitances, find noise figure or noise factor, right? Find noise factor of this, right? And assume matching. Assume input port, right? Very simple to do, but it will kind of give you an idea of the cascaded system noise figure. Okay, and assume that also, okay, you don't have to neglect CLM. So instead of doing this, I would say assume that instead of doing L equal to infinity, so let's say there is an R1 and there is an R2. So that way you can get the noise contribution from R1 and R2 also, right? And find out the total noise figure, and observe noise contribution from M1 and M2 and R1 and R2, given that GM1 R1, let's say, is equal to GM2 R2 is equal to 10, right? So do that yourself. So it will give you a fair amount of idea. So now let's start focusing on how to go about managing distortion, right? So earlier on in the course, we talked about how to reduce noise, and then we went into the aspect of distortion, what happens if you cascade, and various measures of distortion, and so on and so forth. And it's time to talk about how to reduce distortion. One common way of reducing distortion that we have talked about is increasing your overdrive. And the intuition is, if you think about your overdrive, if you think about it's like a MOSFET is like a tap where water is flowing, right? And the overdrive is the amount and you are controlling the flow of the water using a valve, right? The valve goes in and out. So the percentage of the total width of the tap that the valve is controlling is kind of the overdrive, right? So if the valve goes in and out quite a lot, then it is expected that even though you are going to get a lot of change in the flow of water, but the change will also need not necessarily be linear. For example, if you push the valve all the way down, then obviously the water flow will go zero, right? Similarly, if your overdrive goes to zero, your current will go to zero, and beyond that nothing is going to change. So essentially you have to stay away from turning your MOSFET totally off, or in other words of saying the same thing is, you need to ensure that you keep some fraction of this signal swing should be a small fraction of the amount of signal swing should be a small fraction of the available overdrive, Poisson overdrive, and that is something that we saw mathematically also using square law modules earlier, right? Let me give you an analog circuit way of dealing with distortion, right? Reducing distortion, and then we'll in rest of today's lecture I'll probably try to give you a quick and intuitive idea of why that or cannot be used for linearizing RF front ends as is, right? So for example, let's say I have let me take an example and talk about it. So again, I am talking about incremental model. So let's say I have a MOSFET and I connect it in the common source configuration. So clearly this current through it is distorted, right? So this will have GMVI plus some G2VI squared incrementally, right? But now let's say I make an op amp, and this is again R, this is R, and make an op amp, and I put it in negative feedback. Now note that this op amp is also made up of transistors which are non-linear, but let's assume that the op amp has very high gain, right? But has infinite gain. So this is R1. So what is V0 over Vi? This will be equal to R minus R1 over R, right? So this is kind of our first year undergrad stuff. Okay, so this is minus R0 over R under the condition that the op amp has extremely large gain. Correct? So why is this? Why is the op amp, even though this is made up of transistors, not causing any? It's causing minuscule distortion. It's because if you think about it, what is the signal swing here? The signal swing is virtually zero, right? So the input of the op amp is not swinging. The negative feedback, the high gain negative feedback is enforcing a virtual short between the input terminals of the op amp, and hence it is not swinging, right? Because you have limited the swing at the input of your nonlinear devices, right? Input of a nonlinear op amp, hence the negative feedback is ensuring that the output is only a ratio of the R1 and R, which essentially is both R1 and R are linear, hence your output is also linear, even though the forward path having op amp is made up of completely nonlinear transistors, right? So how can I leverage that in the circuit next to it, on the left? So the reason of distortion in this case is because you are having signal swing here. So you have to, if I do not want distortion there, I have to ensure that signal swing goes to zero, right? Which means that if you think about it, that has to be some virtual ground of an op amp, correct? So what can I do? Let me just maybe break it here, and I insert a virtual op amp, just like I have done there, right? And then where should this go? So I know that this current will be linear, because wherever this is connected, if the op amp is in negative, if the loop is in negative feedback, then this current will be linear. But then where do I want this current to flow into? I want this current to flow into the transistor, so maybe I'll connect it here. And the input of the transistor can be driven by the op amp. But wait, is the sense of the loop correct? Let's see. So how do I know the sense of the loop? Let me break the loop hypothetically somewhere. Let me break it here, and I give an excursion here. If this increases, this decreases. If this decreases, this increases, which means the loop is not in negative feedback. So how do I correct it? I basically change the signs of the op amp. So this loop becomes in negative feedback. This voltage is virtually 0, Vi, so this current is Vi over R. So the current through the transistor becomes Vi over, this becomes Vi over, correct? Right? Note that the transistor is still non-linear, but the current through the transistor is Vi over R, because the negative feedback is ensuring that, right? So what has to happen? But because the transistor in its own is an entity which has a nonlinear transfer function between the input and the output, right? Your transistor, if you have a VGS, this is some nonlinear transfer function of VGS, correct? So, but if the negative feedback is ensuring the current through the transistor to be linear, what will be nonlinear? So clearly this will be F inverse of Vi over R, and this will be nonlinear, right? So this is one classical way of ensuring, of an example of using negative feedback for linearization purposes, which various types of these negative feedback based systems are used in analog circuits. The classic block diagrammatic format is this. If this is linear, this is non-linear. Forward path, let's say, is non-linear, and you have a feedback path. This is Vi, V naught. So if f prime of, you can prove that if f prime of this nonlinearity tends to infinity, then this error voltage goes to 0, right? And V naught tends to Vi by beta, right? So f prime is basically the incremental gain, right? I'm not going to prove this, not a part of this course, but intuitively you can get the idea that in the classical A beta feedback model, if A tends to infinity, then your VE will tend to 0 and your output will become Vi over beta, right? But as long as beta is linear, then your input to output characteristics is linear, even though F is a nonlinear block, right? Now this seems to be a magic bullet that we can use to solve any distortion problem. But the key problem here is that in order to have negative feedback or negative feedback based linearization, we must have loop gain be much greater than 1. And why is this an issue? This is an issue because RF systems, it is easier to generate this loop gain of much greater than 1 at low frequencies, right? At maybe few megahertz, maybe 100 megahertz or so. But moment you go to multi-gigahertz frequencies, it is not trivial to generate high loop gain. When I say high loop gain, I mean of the order of 40 dB and 50 dB and 60 dB and so, right? While maintaining stability and all those things, right? So if you have done analog circuits negative feedback loop design, you will readily relate to this. It is not trivial to make high loop gain negative feedback at higher frequencies, simply because you have these capacitors which is which kind of steal current and loads your various blocks, and it reduces the loop gain, right? And you are going to have and there's a classic trade-off between stability of a feedback system and the speed at which you can, and the bandwidth at which you can operate it at, right? So because negative feedback based linearization, even though it's a extremely good way of linearizing a circuit, it is difficult to use in RF systems, right? So difficult to use as is, still can be used as is in RF system due to high frequency of operation, right? Okay. Later on in the course, when we do mixers and when we do transmitters, you are going to see there are some ways of using negative feedback by lowering the frequency, right? But at present, if we limit ourselves to the condition that everything works at RF frequency at multi gigahertz, then very rarely you are going to see systems linearization techniques using negative feedback, right? So let's stop here. In the next lecture, we'll start off from some other linearization techniques, which are if negative feedback based things cannot work, then obviously you'll have to do something in open loop. So we'll talk about couple of ways of linearizing using open loop protocols, right? Okay.